Hi everyone, so we will first compute this. This is the 7th class. So first we see on the clock this time, okay? So you know that after 12 hours it will be seen the same time. So each 12 hours we will see the same time on the clock. That's why we need to compute this. So we need to know what this number 45 is congruent to what modulo 12. Okay, so we see it's 9. Okay, then we add this 9 to this number 12, we get 21. So after this 45 hours we will see 25 on the clock. So for the second question, we will find a formula for this integer that is congruent to an integer a modulo m, and we suppose m is positive. Now to find the formula x, we know x, if such x exists, it should satisfy this. In other words, x is the smallest such number that is the remainder of this division, the division of a by m. Okay, so it is, we can write x as in this form too, where q is the quotient. Okay, as x is the remainder, we can write it in this form. So you know this division algorithm, which is mq plus x. So x can be written in this form, where q is the quotient. So this quotient can be written in this form too, right? This denotes the smallest integer, which is less than a over m. Okay, the smallest integer less than a over m. Okay, so the quotient can be written in this form. Thus, we know the formula for x now. It's this, a minus m times this integer. Okay, now we will find the integer a with this condition. So from this we get that a minus 17 is equal to 29 times k, where k is an integer. Okay, we can rewrite this as in this form, a equals to 17 plus 29k. We know a is in between this interval, so here we have. Now we need to find the values for k to determine the values of a. So we first subtract 17 and get these. Okay. Then what do? We have we divide it by the 29 and get this. So this will be something, some decimal number, real number, which is minus 1 comma ta ta ta, and here we have 1 comma ta ta ta. So k is an integer, then it can be minus 1, 0, or 1 if it's in this interval. So here we have the values of k. We know a equals to this, 17 plus 29k. So we plug k equals to minus 1, 0, and 1 to get the values of a. And here we have these three values. Now for 5, we will find the prime factorization. So to find a prime factorization of a given number, you just start with the primes, the first prime, which is 2, then the second prime, 3, and you continue like this. If you find a number, a prime that divides the given number, here we have 7, for example. This is the first prime which divides this. Then we write as in this form, okay? So here we have the quotient. Now what do? We do the same method for this number now. So it is divisible, it is not divisible by 7, but 11, okay? After 7, the first prime we found which divides this number is 11. Then we rewrite it, this number, 143, by dividing this. So we get 11 times 13 for this number, okay? And we had before 7. So here we have the prime factorization of this given number, because 13 is already itself a prime. We don't have to do anything, so we have this. So here we have a definition of a perfect integer. We say a positive integer is perfect if it equals the sum of its positive divisors other than itself. This part is important. So we're given here two numbers, 6 and 28. We will decide, actually, we will show if they are perfect. So this part is homework for you. I will just show that. So we can write the prime factorization of this number 6. Okay, not the prime factorization, just the factorization. So here we have 3 factors of 6. We don't count 6, right, as it should be other than itself. So we have these 3 divisors. We add them and get 6 itself, so it's perfect. You do the same thing for the second number, okay? So we will show now that this number is perfect when this is a prime. So if it's a prime, then there is no number which divides this prime number, right? So first recall that. Then what are the positive divisors then of this number? You know, one divides anything, so we have 1, then 2, then 2 squared, then till 2 to the p minus 1. As you see here, 2 to the p minus 1. Then any power of 2 which is less than p minus 1 will be a divisor of this number, so we count them. Now we have also this prime number, 2 to the p minus 1, so we count them 2, we counted 2. So what else? Then if 2 and 2 to the p minus 1 divides this number, then this product also divides it. Okay, we have this. And again, 2 squared divides it, and this divides it. So we have this factor 2, this divisor 2, sorry. So till here, we have all divisors. We don't add 2 to the p minus 1 times 2 to the p minus 1 because it's itself, it's the given number. That's why we don't count it. Okay, so we have all divisors of the given number. Now, what do we do to check if it's perfect or not? We need to add them. We need to find the sum of these divisors if it gives us the given number or not. So we add them. Okay, now here we have 1 plus 2 squared plus 2 to the p minus 1, and this plus, now we distribute this 2 into the parentheses and get 2 times 2 to the p minus 2 here. 2 times 1 gives us minus 2. Do the same thing for the rest and get this. Okay, now here we have 2 to the p minus 1, and here we have plus 1. So they will we will simplify them and get 2 to the p there. Okay, for this and this, 2 and 2 times 2 to the p minus 2, we will get 2 times 2 to the p. Till here, we will get 2 to the p minus 2 times 2, okay? So we will simplify with this here. It will be 2 to the p minus 2 before this number. And here we have minus 2 to the p minus 2. So they will be simplifying again. And here we have. So as we don't have the number itself here, so we don't have 2 to the minus 2 to the p minus 1. So we have here this number, okay? Now we rewrite these ones in the parentheses of 2 to the p and get this, and still we have 2 to the p minus 1. Okay. Now what do we have? We can rewrite this sum as in this form. You need to check it, okay, by yourself. So we can rewrite this sum as in this form. Now here we have 2 minus 1, which is equal to 1, and we have finally 2 to the p times 2 to the p minus 1 plus this number again. Now what do? We distribute it again and get this sum, okay, in here. So we rewrite this, okay. We rewrite this as in the parentheses of t2 to the p minus 1. Here we have 2 to the p, that's here, and we have minus 2, and here 1, okay. So this gives us 2 to the p minus 1. So this is the given number actually. So we find the sum of its divisors, positive divisors, and get itself, right? So it is a perfect number by definition. Now we're given this function, Euler phi function, okay? So it is the function that gives the value at this positive integer n, the number of the positive integers less than n or equal to n that are relatively prime to n, okay? Now, for a basic example, we find the value of 10, the value of phi at 10, okay? So what are the positive divisors of 10? Here, sorry, what are the numbers that are less than 10? Here we have these numbers, including it, okay, including 10, we have these numbers. Which ones are the numbers which are relatively prime to 10? So here we have 1, 3, 7, and 9, right? So these are relatively prime. Then we have 4 numbers which are relatively prime to 10, right? So phi of 10 is 4. Now we show that n is prime if and only if phi of n equals to n minus 1. Now first suppose that n is a prime number and show this equality, okay? Now as n is a prime number, then each number which is less than or equal to n is relatively prime to n, right? Except that. So the number of these numbers, this set actually, the number of the elements of this set is n minus 1 because okay, it's n minus 1, so phi of n is equal to n minus 1. Now suppose the opposite. So suppose phi of, not the opposite, but sorry. Suppose phi of n equals to n minus 1 and show n is a prime. Now what do? We know phi of n equals to n minus 1. So the numbers that are less than n and relatively prime to n are this many, n minus 1 many, which means that there are no number that is less than n that divides n. So it means n is a prime, right? So we show the other side too. Okay, so we know now n is a prime if and only if phi of n equals to n minus 1. Now we prove this one. We will compute phi of p to the k when pi is a prime, okay, and k is a positive integer. So this function phi counts the numbers that are relatively prime to p to the k, okay, which are less than, of course, which are less than p to the k, and relatively prime to p to the k. Now it can be computed by this actually. So the number of the elements of this set, which includes the numbers n that are less than or equal to p to the k. So the number of the number of the numbers that are less than p to the k. This set gives us that. Now what about this? And this gives us the number of the elements that are not relatively prime to p to the k. Okay. So if we subtract them, we will obtain the numbers that are less than p to the k and relatively prime to p to the k. Okay, so actually exactly the definition of this function phi. So this is clear, right? The number of this set, the number of the elements of this set is p to the k. Now, what are these elements? What's the number of this set, the elements of this set? So we know p is a prime. Then if we have this, then we need to have p divides n. Okay, so as p is a prime, then the only divisors of this p to the k are the multiples of p, as in here. Okay, and how many elements are there? It's p to the k minus 1. So the number of the elements of this set is p to the k minus 1. Here we had p to the k, then phi of p to the k is p to the k minus p to the k minus 1. Now we will use the Euclidean algorithm to find this greatest common divisor. So what do? We pick the bigger number, with the greater one, okay, and divide it by the less one, okay, and here we have the remainder, which is 90. Now what do? We take this, okay, and divide it by the remainder, and here we have again another remainder. Now we take this one, 90, and divide it by this remainder and get this. Again, take this 21 and divide it by the remainder and get 3. Then we do the same thing for the last time and get 0. Now, if you have 0 here at the end, then the previous remainder, which is 3, is the greatest common divisor of these two numbers. Okay. So here we found, by using the algorithm, the greatest common divisor of these two numbers. Now for this one, we will use Chinese remainder theorem. Okay, we are given the system. Now this is the first step. So, okay, let me write it. This is the first step. So what do? You write capital N by multiplying each of these ones, so that they are these modulos. Okay, this, and this. Okay, you first compute it. Now, then what do? You do? You find yi's, okay, by n over ai, and ai's are these ones. Okay, so a1, for example, is 1, a2, a3, and a4. Okay. Now you find yi's. Okay, for example, y1 is n 330 over 2. Sorry, ni. I mean, sorry, not let me clear that. Okay, ai is 2. Sorry, a1 is 2, A2 is 3, A3 is 5, and A4 is 11. Okay, these are AIs, these ones. Okay, so we computed and by multiplying them. Okay, now we have y1 here, y2, y3, and y4. Okay, now what do? We find the inverses, modular inverses of these yi's. How do we do that? So for example, first of all, you need to know the definition of modular inverses. So if we say zi is a modular inverse of yi, if we multiply them, we first multiply them, then if this this product is congruent to 1 to modulo congruent to 1 modulo ni, then we say zi is an inverse of yi. Okay, modular inverse of yi. Okay, so this is AI. Okay, here we have. So the modular inverse of this number, which is y1, is this one, z1, such that it's congruent to 1 modulo 2. Okay, what's it? So you see this is congruent to 1 modulo 2, then z1 is 1. And for z2, again, you compute it in modulo 3, and you get 2, then z2 equals to 2, because you multiply them 4, you get 4, and it's congruent to 1 modulo 3. Similarly, you obtain the rest. Okay, z1 here, z2, z3, and z4. Now, then the solutions of the system is given by this, are given by this. So you multiply this one. So 1, this is 1, times y1, okay, times z1, okay. And then you add 2. Here we have 2. Then this y2 and z2, which is 2. Then 3 and y3, then z3. And similarly y4, z4, and here we have 4. And you get this. This should be, which is x, okay? Sorry. Which is x. This should be congruent to sorry, I made a mistake there. So it should be, I made a mistake there. So here we have this. I forgot to write that. So we have this number, then we obtain x is congruent to this number modulo this, capital N. Okay, remember we counted that before. So here we have this equality, okay, for some integer. So these are all solutions to the system, okay. So we will use Fermat's Little theorem to find this one, okay. So it says we have this congruence if P is a prime and A is not divisible by P. So we say 41 is a prime and 23 is not divisible by that. So we have this congruence by the theorem, okay? So we plug P equals to 41 and A equals to 23. So we have this. Now, we see we need to compute that. So what about this power? If we divide it by 40, as in here, we have, if we divide it by 40, we get 2 as the remainder, okay? Now, then this number can be written in this form. So it is congruent to this number modulo 41, okay? Now, this number also bigger than that, so we compute it again. So it is, if we divide it by 41, the remainder is 37. So this is congruent to this number, modulo 41. Okay, by using the theorem, we easily obtain this. Now, for this one, we will use, as in the question, the inverse of this number, 144. Okay, first we find its inverse. So then we will multiply this congruence by its inverse and get easily the number x. Okay. So to find the inverse, we will use Euclidean algorithm first. Okay, we write it. So then we will write a linear combination of them, which is equal to 1. So 1 can be written from this equality 3 minus 2. Instead of 3, we can write, instead of 2, we can write 5 minus 3. And for example, instead of 3, we can write 5 minus 2 again. Okay, then we have 5 minus 2 times 2. Then instead of 2, again we write 5 minus 3 and get this. So we have minus 1 times 5 plus 2 times 3. Then instead of 5, we write 13 minus 8. Okay, and instead of 3, we write 8 minus 5. And we do the same things for a few steps, then obtain this equality finally. So we get 1 equals to this 233 times minus 55 plus this. So it gives you that 89 is the inverse, modulo inverse of this number. Okay, so you can use this one to get the inverses. Okay, so this is the inverse of this number, 144. So we can multiply this congruence by this number. Okay, if we multiply each side, we get this. So as this is the inverse of that, then it's congruent to 1 modulo of this. So we have x is congruent to this number, which is 356, congruent to that. So again, we divide it by this number and get this. So we can write x as in this form, right? We just use this last congruence, okay? So for any integer, we can write it as in this form, okay? By using the inverse of this number, we get this variable, okay? This was the last question. You can attend the office hours, which is on Fridays, okay, between 5 and 7 p.m. So see you there. Hope to see you there. So take care.